Welcome everyone to the 2026 Photonics Spectra Summit Series. Thank you so much for attending the Laser Test and Measurement Summit. And in this session, you'll hear from Mateusz Ibek, the product manager for ultrafast laser diagnostics at APE. Mateusz has a background in physics and has spent nearly a decade developing autocorrelators, spectrometers, and other laser diagnostic tools. Today, he joins us to highlight state-of-the-art diagnostics for the characterization of ultrafast optical pulses. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me. Mateusz, we appreciate you for taking the time to join us here at the Laser Test and Measurement Summit.
Thank you, Jake. Thank you also for the opportunity to being able to present I think a very interesting topic for everyone that uses ultrafast lasers. Let me make that increase it. So yes, I'll be presenting some of the most used state-of-the-art diagnostics for characterization of ultrashort pulses. First of all, of course, I want to give you some motivation, try to explain why it is even important or necessary to measure pulses, laser pulses, show some use cases and their impact, and then I come to current technologies and commercially available technology, the current techniques and commercially available technology. And finally, I'll talk about measurement uncertainties and their traceability or measurement traceability, as well as some challenges in outlook. So let's just jump in. Why is it important to have laser diagnostics? So you can control what you can measure. The pulse leaving your laser may differ significantly from what theory predicts. So that's why there's kind of 4 logical steps. So you have to know your light source and its pulse characteristics. You have to define the process or experiment input that you have and use. Then you have to control and adjust the process or the experiment, of course, and verify the process or experiment, the output. And for these steps in between, there's the diagnostics or measurement devices to allow you to control and adjust the process and verify the process. So some basic laser physics, this is very basic indeed. There's more to it, but just for your general overview. On the left side, there is a perfect Fourier transform limited pulse with an autocorrelation in white. The red, green, and blue waves, that's the Fourier components or some of the Fourier components of a laser pulse, which consists of many different wavelengths. And as you can see, when we go through air, through glass, through some coatings, or basically any optical component after the laser, with laser pulse, the pulse is chirped. Typically it's 2nd order dispersion or even 3rd order dispersion, which in the easiest sense or easiest way means that the different components arrive at a different time. For example, red arrives first, green a little bit later, and blue components even later. This will be a positively chirped pulse, and what it does is it broadens, in this case, the autocorrelation. So we have a Fourier transform limited pulse, we have some optics in between, we end up having a broader pulse. That is mostly or almost always what is happening. The shorter the pulse is, the more effect it has. And that's why we need diagnostic devices to measure this. Where is this mostly important? There's many fields. To name some, is for example ultrafast spectroscopy, where pump probe and 2D spectroscopy require sub-cycle precision only. So wrong pulse duration means wrong dynamics. At science and high harmonic generation require up-to-second pulse trains and isolated pulses with a CEP control and temporal gating verification. Most people will probably work or know precision micromachining or some material processing with lasers, where ablation quality is pulse duration sensitive. So femto versus picosecond regimes show very different results. Or for example, this is a very sensitive area is the medical and ophthalmological area. For example, cataract and corneal surgery with lasers rely on reproducible pulses. Duration drift affects depth and quality of cut. In the worst case, the eye is only heated and not processed properly. Same is another important area or case is, for example, the optical time division multiplexing in telecom and data links, and it needs accurate pulse width control, for example, at 100 gigabits and beyond. Also, quantum optics are sensitive to pulse duration changes or pulse parameters. So, for example, entangled photon generation in nonlinear waveguides requires spectrally pure, well-characterized pulses. So these are just some examples. There's many more. I will now show a few and explain them in more detail. So, for example, in the context of medical or imaging, we start with a laser. We have a very short laser pulse width, which is defined typically as full width at half maximum. That can be seen in the left graph. So the blue one is the blue is a perfect Gaussian pulse, a short pulse, and or a transform limited Gaussian pulse, and it travels through some optical system like a microscope, for example, optical components, and in these components dispersion occurs. So at the imaging plane we have a longer pulse, and or in the imaging plane or the machining object or the patient in case of ophthalmology, for example. And in imaging, for example, this means less sensitivity, a compressed image, low contrast in your image, worse machining quality, edges are cut, for example, not evenly, and it goes even to potential tissue or material damage. That's why in these cases or in these use cases, in this context, it's very important to measure the pulse before and after the optical setup to make sure that it's conditioned properly to be the shortest possible. Even more sensitive, as I said, is ophthalmology, and we have here an example that is happening often. It's we have the same pulse with two laser pulses, blue and red, same pulse width, but one has wings which come often from, for example, uncompensated high order dispersion or cell phase modulation in fibers. And with these wings mean that the pulse quality is worse, so the pulse energy is dispersed over a longer time, and the peak power is different. This is here normalized. So we have a difference in nonlinear processes, for example, like ablation or cutting, and we get heating effects, although the pulse duration seems to be the same. And a very strong case is pulse quality or pulse background. On the left side, you can see this graph with the red and gray curves. The pulse duration in this case is more or less the same measured with a standard autocorrelator, but the gray curve displays are very, very high and very long pulse background. So, for example, if these lasers are measured with a power meter, they may show both 20 watts output power, average power, but the pulse energy or peak power of the red laser will be much higher, and the pulse energy or the peak power of the gray laser will be dispersed over a longer time, and this energy only leads to heating. So we have a short amplified pulse and a long energy background, which leads to low peak power and therefore to low efficiency and sensitivity and heating, for example, instead of ablation. So these are some cases where we can see that a standard autocorrelation, for example, or the specified pulse duration is not the full information that we can get from a laser. And by measuring with different methods, with different autocorrelators, we can control the process better and also know better how the pulse is conditioned in reality. So we have in a laser several pulse parameters that we can measure, namely the pulse duration. That's the simplest parameter or the most known parameter, the spectral width or the spectral bandwidth and its shape. We have the time bandwidth product, which tells us how far or how close the pulse is to Fourier transform limit. We have the chirp and the phase, and spectral and temporal that tells us about the frequency distribution within the electric field of the pulse. And we have the peak intensity and its shot-to-shot stability. So the shot-to-shot stability is most important for kilohertz or amplified systems. There's also the spatial profile that is important for focusing, but I won't go into further detail on that since this is about the temporal and spectral properties of the lasers. Okay, so in the temporal intensity range of measurements, we have a few autocorrelation techniques, namely intensity autocorrelation, which is basically the intensity profile of the overlap of the two pulse replica inside an autocorrelator. We have the fringe resolved autocorrelation. There's an example on the left. This is also the same autocorrelation, but it is a little bit a different setup, and the modulation comes from the interference of the laser wavelength of the pulse. We have single shot autocorrelation, which requires only one pulse to be measured, whereas the intensity in fringe resolved autocorrelation, for example, are scanning techniques, so they integrate a lot of pulses into an intensity curve. And as maybe a side technique is the cross correlation, which means we don't send just one beam with one wavelength into the autocorrelator, but two different beams with two different wavelengths and correlate these two. This is typically used when one wavelength is not accessible. So for example, at UV wavelengths, second harmonics crystals don't convert the wavelength into even higher wavelength because the crystals become opaque to this wavelength. So one uses some frequency generation, or in this case, difference frequency generation with a cross correlator. The most known and used techniques for spectral and temporal intensity and the phase are spider, frog, and D-scan and D-shot. On the left side is an example of a frog trace or frog measurement. It measures the pulse duration or the autocorrelation consecutively for each wavelength component of the spectrum. Therefore, it is a 2D graph. The same, for example, is true for D-scan D-shot. This is a dispersion technique where the second harmonic light is measured relatively to a dispersion that is introduced into the beam. And of course, spider, which is also a single shot technique or multi-shot technique, where the full spectrum and the phase intensity and phase of the pulse is measured. So I have prepared a table with all these techniques and all their properties and their measurement capabilities, as well as some specifications at which these techniques work. So first of all is intensity autocorrelation or single shot autocorrelation. They are quite similar because they measure the nonlinear signal versus the delay. This can be type 1 second harmonic, type 2, or third harmonic. It only measures the pulse duration, and but it is very simple and robust. So since it only measures the pulse duration, it cannot retrieve phase or full shape. We have to assume the shape in this case because the autocorrelation is a convolution of two pulse replica, and through fitting it has to be retrieved, or through fitting it has to be guessed how long the pulse was. The better the fitting, the better the guess of the pulse duration. The range in which this works, laser specification range, is quite wide. It's around 5 femtoseconds to 500 picoseconds or more. It is single shot capable. It goes to gigahertz repetition rates. Wavelength ranges. The longest that we can measure with autocollators is 200 nanometers to 12 micron, and sensitivity is in the picojoule range. The interferometric autocorrelation is basically the same as intensity autocorrelation, but the two beams interfere with each other, creating the interference pattern. And therefore we get the pulse duration, but also limited phase info from this interference. So it has a higher sensitivity to pulse structure, but is also phase ambiguous. It is limited to near transform limited pulses, and its specifications are very similar to the intensity autocorrelation. So 5 femtoseconds are the shortest pulses. 1 picosecond is around these are approximate numbers. 1 picosecond is the longest pulse duration that can be measured. This has to do with the fringe interference pattern and its resolution. So the repetition rate is again hertz to gigahertz, 200 nanometers to 12 micron, and picojoule sensitivity range. And the third autocorrelation, or the third correlation method, is the cross correlation, where we combine two different laser beams with different wavelengths and different properties. So we use the nonlinear signal from a test and a reference pulse. It gives us only the pulse duration in certain combinations. When one very short pulse with a long pulse is combined, it can give us the shape and the timing of the two pulses relative to each other. So this is useful for timing or jitter measurements. It requires two laser pulses, so it requires a reference pulse. And the specifications are very similar, or again, almost the same as for autocorrelation. The more sophisticated methods that give us also the spectrum, spectral shape, and phase and temporal shape are SPIDER, FROG, and D-scan. So starting with SPIDER, which stands for spectral phase interferometry for direct electric field reconstruction. It is a spectral shearing interferometry, which combines two pulses. One is dispersed through material. They are interfered with each other. It is a direct measurement of the electric field, and it gives us full temporal spectral intensity and phase. Since it's direct, it's fast retrieval the retrieval is fast. It has a limited spectral resolution because it uses standard spectrometers, and analytic integration of the interferogram yields the spectral phase. SPIDER retrieval is non-iterative. 5 femtoseconds to 1 picoseconds, single shot to gigahertz again, around 500 nanometers to 1200 nanometers, since this is relying on silicium spectrometers typically, and the nanojoule range in sensitivity. FROG is frequency resolved optical gating. It's basically the autocorrelation, but resolved in temporally resolved. So it's a nonlinear spectrogram. It can be done with second harmonic, third harmonic, transient gating. There's different methods to do that. It gives also the full temporal and spectral intensity and phase, except the difference to SPIDER is it's time ambiguous, so you cannot tell if a post pulse is a post pulse or a pre pulse, for example. SPIDER has the temporal arrow or the temporal direction, whereas frog doesn't have that. It is a complete characterization. It is typically an iterative retrieval, so the electric field has to be calculated in a few iterations from the frog trace. And it is typically computationally intense. So it takes seconds to, or some time to retrieve the frog trace from the, retrieve the frog signal from the trace. The typical specifications are 5 femtoseconds to 1 femtosecond, single shot to gigahertz, again 400 to 2000 nanometers, and picojoule range. And finally, the D-scan or dispersion scan from the company Sphere Photonics. In this case, the second harmonic signal is created, and the dispersion of the signal is manipulated, or there's a dispersion introduced into the signal, and it's the nonlinear signal is recorded. It gives also full temporal spectral intensity in phase. It is very robust for few cycle passes, but it requires also relatively short passes compared to the other techniques. It's a simple setup, not very cheap because of 2 spectrometers required, and it requires a calibrated dispersion element. So specifications are around 4 femtoseconds, but even shorter than that, to 400 femtoseconds. Signal shot to gigahertz and 450 to 700, 1700 nanometers. So given these techniques, what are the uncertainties of these measurements? Typically, these uncertainties are around 1 to 5%, based on different factors, but with comparative measurements and theoretical considerations, these uncertainties can be reduced or kept at bay. Systemic errors, particularly at very short durations, can increase uncertainties sustainably. I call it this the geometric regime. This is the case when the pulse duration in time or in space is comparably wide to the width of the laser beam, and the the spatial properties, practically in temporal properties, become very comparable in dimension. Common sources for errors are material dispersion, cell phase modulation, for example, in fibers, intensity noise in the measurement in general, and algorithmic constraints, as well as spatial parameters like pulse quality, for example. Assumptions in any of these domains, for example, temporal pulse shape, need to be validated to prevent misleading measurements. So how about traceability? How do we know that these devices measure correctly? Traceability for temporal measurements can be established via length standards, for example, material constants and traceable length measurement, like interferometric wavelengths reference from known light sources. We at APE, we are compliant with the German industrial norm 58175-2. This is the German Institute for Standardization, and it published a document in 2021 for the characterization of ultrashort laser pulses. We are also working actively on the ISO norm, which is coming soon. This will be the international norm for the same purpose, for the characterization of laser short pulses. And for our devices, we use, for example, stabilized helium-neon lasers, or helium-neon laser frequency as an interferometric length standard to make calibrations. NIST traceable. NIST is the National Institute of Standards in the US. On the right side, you can see, for example, so we have the laser frequency in blue, helium-neon laser, and scanning or interferometer scan of this frequency fully transformed into frequency. And these two curves deviate a little bit. So by calibration, we match these two curves, and then we know that our delay systems that measure the pulse duration are absolutely precise to less than 1% uncertainty. So to sum up and come to an end, I would like to give an outlook on these technologies, what we are working on, what I believe are the technology, where the technology is going. So better standards and calibrations are necessary, like this, for example, going from the national standard to an international standard. Since there's many devices on the market, they need to have better standards or apply to better standards to make reliable measurements. Of course, we are thinking of and working on the reduction of cost complexity. Of course, I think everyone is interested in that. Then the trends go also to system integration for constant monitoring and feedback. So lasers, for example, with integrated autocorrelators. Fast and high repetition rate pulse monitoring, where every single pulse can be measured, are important. And the same is true for even higher sensitivity for low light applications like telecommunications lasers that are very have very weak intensities. So improving sensors for these applications is another field we work on. So thank you for listening, and that's from my side.
Thank you so much, Mateusz, for presenting on state-of-the-art diagnostics for the characterization of ultrafast optical pulses. Before we wrap up here, I just want to remind everyone in the audience, if you haven't already, you can go ahead and type your questions and comments into the Summit chat box. And do not worry, if you have not gotten a response yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Laser Test and Measurement Summit. Thank you all so much for joining us.